next we ask, can we define product of two vectors? The answer is yes, but before doing that I will take a slight digression, and now we will go into vector algebra representing them by numbers and in a different way algebraically. So, first let us represent vectors in an algebraic way, and then we will be able to define the product of two vectors properly. Not only that, representing vectors in an algebraic way would make addition and subtraction of two vectors easy when we have many vectors. So, for that, first I introduce the concept of unit vector. A unit vector is a vector of magnitude 1. So, let us say unit vector n, and to show that it is a unit vector we make a hat on top of the vector. This magnitude is going to be 1, and it could be any direction representing the vector in that particular direction. In particular, now we will take the x, y and z axis, a Cartesian coordinate system, and define unit vectors in x direction, call it I, unit vector in y direction, call it j, and unit vector in the z direction, call it k. Now, any vector can be written as a, what I call the x component of this vector, times I plus a the y component of this vector j plus a z and the z component of this vector k. So, this is known as the z component, y component, x component. You can see that what we are doing is multiplying this unit vector by a x. So, this will give me a x times this, a vector in this direction, let us say this a x I, and I add this to a y j. So, I will draw it parallelly here. This will give me a x I plus a y j, and on top of it we will add say a z k. I move it here parallelly. So, the net vector A would be something like this. This is a z k. Although in this case I added a x and a y first and then a z and got this vector, it does not matter in which order you add these vectors, because we have already proved that addition of vectors is commutative. So, I could have added a y and a z first and then added a x, I will still end up with the same vector a. So, now the meaning is quite clear. When I write a equals a x I plus a y j plus a z k, I am writing a vector a x times I pointing in x direction, a vector a y times j of magnitude a y pointing in y direction, and a vector of magnitude a z pointing in k direction, and adding them all up, and that is the vector a. A x is called the x component of a, and a y the y component, a z the z component. So, let us see, suppose I have write a vector v is equal to I plus 2 j plus let us say 3 k. How would it look? X, y, z. So, I would make vector I unit vector in this direction plus 2 j would be a vector of magnitude 2 in this direction. So, this would be I plus 2 j, and 3 k would be of magnitude 3 in this direction. So, up to this point. let us make this vector here, this, then summation of all three, this vector would be I plus 2 j plus 3 k. How about the magnitude of this vector? You can see that I can first add these two, get the magnitude of this, that would be a x square plus a y square square root, and then again add a perpendicular vector to it, which will be a z. So, the net magnitude would be square root of this component, which is a x square plus a y square, and then a perpendicular component a z, add them all up and take the square root. This is the magnitude of the vector, and you can see that direction is easily seen and visualized by making the vector using these unit vectors. Having written a vector in its algebraic form, let us ask, how do I add two vectors? Suppose there is another vector b, which is b x I plus b y j plus b z k. When I add the two vectors a plus b, you can see graphically and carry it out that the net vector would have an x component, which is the summation of the x components of individual vectors. Then I add the y components of individual vectors, and then the z components of the individual vectors. Similarly, minus b would be nothing but each component of the b vector would become negative. And therefore, a minus b, which is nothing but adding a and minus b, would be same as a x minus b x I plus a y minus b y j plus a z minus b z. Okay. Having written the vectors a y j plus a z k and b as b x I plus b y j plus b z k, we are now ready to write their products. All possible combinations of the products are a x times b x, a x times b y, a x times b z, similarly a y times b x, a y times b y, a y times b z, and a z times b x, a z times b y, and a z times b z. These are all possible products of different components of the two vectors, out of which ones do we take? Which ones do we define as vectors and scalars is the next task that we are going to address. You already know from your intermediate 12th grade that there are two kinds of products: a dot product, which is a scalar product, which is given as the sum of a x b x plus a y b y plus a z b z, and the cross product a cross b, which is a vector quantity, which is given as a component a y b z minus a z b y in x direction plus j a z b x minus a x b z in y direction plus k, the component in z direction is a x b y minus a y b x. But as I showed you on the last slide, there are these all possible products which are being taken here, but why do we take them in this particular combination? Why do I define this to be a scalar product? Why do I define this to be a vector product is the question that I want to address now, so that we get a better understanding as to why the products of these two vectors are defined in such a manner. And for that I want to look at another property of vector quantities, and that is the change of vector components under rotation.